Hello, in this video I'm going to show you how to use the ideal gas law and especially how to find the number of moles of a particular gas. How do we work that out? The ideal gas law is really important. PV equals nRT. This just summarizes so many things about gases. Do you need to remember it? No, it's on the formula sheet. So you'll be given this in every assessment task you do. PV equals nRT. You won't really use it much in year 12. It's mainly in year 11. In the equation there you can see R, the gas constant, and that is given to you as well on the sheet, 8.314. And you won't use that gas constant except in this equation. That's the only time you'll use the gas constant R. And you won't use this equation really in year 12. But it is important in year 11. The units are important. So we've got PV equals nRT. What are the units for all these things? Pressure is in kilopascals because of the constant that you're given. It could have been pascals, but because of the constant they're giving you, it's kilopascals. Now, you won't use pressure much at all except in the ideal gas law. So kilopascals are not a big part of this course. You won't use them in year 12, but just for the ideal gas law, use pressure in kilopascals. And if I was setting a question, I would always give it to you in those units. This is not one where we want to trick you and give you pascals or something and you have to convert it. It's not that important. It's only used here. The volume needs to be in litres. That is important. Always convert to litres. Number of moles, the amount is in moles. Temperature, now here's something important that we will use later on. Temperature is in Kelvin, and that's going to apply in all the formulae that you use, not degrees Celsius, but Kelvin. Now let's think about what Kelvin actually is. I've got two scales here. One is Fahrenheit, the other is Celsius. Fahrenheit has these weird numbers. Water freezes at 32. Boils at 212. Why such funny numbers? It was based on how we feel as people. 0 degrees on Fahrenheit was defined as a temperature that we find very cold. 100 is we find it very hot. That's a hot day. It's hit 100. So 0 to 100 was a measure of how pleasant and comfortable it is for people, from very cold to very hot. When we did Celsius, we didn't link it just with something subjective like how warm it feels to you. We linked it with something more objective, the melting point and boiling point of water. That's why on the Celsius scale, water freezes at 0, it boils at 100. So Fahrenheit is like how it feels for a person. Celsius is like, what's it like for water? 0 is really cold, it freezes. 100, it boils. And most temperatures that we work with are 0 to 100. So what did they do with Kelvin? Well, what's it like from the point of view of an atom? And what feels cold for an atom? It turns out, theoretically, if you could cool down a substance more and more and more until there's no heat energy left in it and the particles theoretically stop moving, you would reach the absolute lowest possible temperature. And when we project it all back and work that out, we come to a particular temperature, which turns out to be minus 273.5 degrees Celsius. Just look at the one on the left. If we could cool things down to minus 273.15 degrees Celsius, theoretically, all the motion would have stopped and it's as cold as it could be. So from the point of view of the atom, that's as cold as it gets. So that's what, and of matter, all matter, not just the atom. So we define that as 0 on the scale in Kelvin. And everything goes up at the same sort of scale as Celsius. So 1 degree Celsius is the same as 1 Kelvin, but it starts at a different point. Now, when you work that out, it means that 0 degrees Celsius turns out to be 273.15 Kelvin. And 100 degrees Celsius is 373.15 Kelvin. So how do you convert from degrees Celsius to Kelvin? Notice I'm not saying degrees Kelvin. We used to, but they've changed it, just Kelvin. How do you change from degrees Celsius to Kelvin? You've had to add 273.15. So that's all we do. Kelvin is the temperature in degrees Celsius, add 273.15. Do you have to remember that number? You don't. Once again, the formula sheet has it on there. So when they're giving you the volume of 1 mole of ideal gas, they tell you at 0 degrees Celsius, which is 273.15 Kelvin. So you can just look at the data sheet and that reminds you that to get from Celsius to the Kelvin, you add 273.15. So those are the units for the ideal gas law, PV equals nRT. And you substitute those in, you can work out all sorts of things. The form it's given to you in is PV equals nRT, and you need to rearrange that depending on what you're working out. It's easier to rearrange first because you're going to have some pretty funny numbers that you're substituting in. So if you're asked to find pressure, you just divide both sides by volume. You get pressure is nRT over V, and you can then substitute it in and find your pressure. If you're asked to find volume, divide both sides by P, and you get a different form. If you were asked to find the number of, now we'll do a different order, the temperature, you divide both sides by nR, and you get this form. If you were asked to find number of moles, divide both sides of this by RT, we get this form. And that is very useful because that means if you have any gas at a particular pressure and volume and temperature, you can work out how many moles there are there. And remember, we often want to work out how many moles we've got. How do we use all this? Two ways that you can find the volume of a gas. On the data sheet, it tells you the volume of 1 mole of ideal gas at 0 degrees Celsius and 25 degrees Celsius at 100 kilopascals, which is about our normal pressure. So, since we know that, if the gas is at 100 kilopascals, normal pressure, and it's at either 0 or 25 degrees Celsius, you can just use that volume from the data sheet to find how many moles you've got. And the moles you've got is just the total volume divided by the volume of 1 mole at that temperature. For example, at 25 degrees Celsius, the number of moles you've got is just the volume of your gas divided by 24.79. It's really quick and easy. If it's not at that temperature and pressure, then you need to use the ideal gas law, PV equals nRT, and to find moles, you'd use the rearranged form, N equals PV on RT. Now, what if they tell you it's 100 kilopascals and they tell you it's this temperature and you don't notice and you go and use the ideal gas law? It still works, you get the same answer, it's just more complicated, more chance of making a mistake. So if they tell you 100 kilopascals and 0 or 25 degrees Celsius, one of those, the moles is just the volume divided by whatever the data sheet tells you is the volume of 1 mole. If they give you a funny number of pressure or temperature, you use the rearranged PV equals nRT, the ideal gas law. And we'll give you some practice at that. They are important, but you won't use the ideal gas law a lot beyond year 11. It's mainly a year 11 concept.